Okay, in this lesson we're going to continue to look at linear inequalities, but we're going to apply them and finally to cases or word problems that may help us understand why we've been doing linear inequalities up to this point. What we've noticed right now up in this lesson is that linear inequalities are represented on a coordinate plane, and we generally have a boundary line, and one side of that boundary line, one half of it, represents all the possible solutions. So we looked at how to create the boundary line, and then how to use a test point to determine which half of that boundary is part of our solution set. If we look at this word problem, we're going to kind of see the same thing in an interesting way. This problem states a sports store has a net revenue of $100 on every pair of downhill skis, so they make $100 on every pair of downhill skis and $120 on every snowboard sold. The manager's goal is to have a net revenue of more than $600 a day from the sales of these two items. So what we're going to do is represent all the possible combinations. That's what an inequality does. It can represent many combinations that would meet the goals, or in this case, the manager's goal of to have more than $600 a day from sales. So first thing we're going to do is define the variables. The two variables here are how many skis they sell and how many snowboards they sell. So I'm going to use K because they both start with the letter S, so we're going to choose some other variable. K is going to represent the number of skis sold. The next thing I'm going to do is have N, because it's the second letter in snowboards, represent the number of snowboards sold. I'm actually going to skip straight to the graph and show you an alternative method of doing this if you don't know how to come up with the linear inequality, and then we'll look at the linear inequality. One method of coming up with the boundary line is if we take the manager's goal but take out any of the inequality language, or the more than, less than, greater than, all that type of language. So if I wanted to know the boundary line, if I took this more than out, we're going to put it back in a second, but that's going to help me come up with the boundary. So let's pretend that the manager's goal is to have a net revenue of $600 a day. And come up with, like we've said, the boundary needs 2 points. So if we could come up with any 2 points, so the boundary could be any 2 points where the net revenue equals $600. Well, there's a couple of obvious ones. Would be, what if we had that the manager sold 6 pairs of skis and 0 snowboards? You should label the axes. It doesn't matter which you label them with. I'm going to label the x-axis as skis and the y-axis as number of snowboards. So one way to have $600 in revenue is 6 skis and no snowboards, and that represents this point right here. That would be 6 skis and 0 snowboards. Another possible one would be, what if I sold 0 skis and I sold 5 snowboards, because 5 times $120 of the revenue is equal to 600. Those are 2 ways, and that would be right here. Those are 2 methods to get an exact revenue of $600. That's actually your boundary line. Now, since we can talk about if that boundary line is going to be included or not. Since the manager wants more than 600, it's not allowed to equal 600. That would actually be a dotted boundary line because it's not included. So that would be this. So here's sort of our boundary line here. Now the next thing we need to determine is which combinations would satisfy which half of this boundary line would be included. Well, if the manager wants more than $600 a day, would a point like this, 0, 0, 0, so 0 skis and 0 snowboards, would that meet the manager's goals? If the manager's goal is to have a net revenue of more than $600 a day from sales of these 2 items, well, if he sold nothing, he's making $0, which is not meeting his recommendations. So that means that the other half would meet his goals. Okay. The last thing to do is to recognize that some parts of these, we need to look at the restrictions, because you can't sell a negative amount of skis. So any of these quadrants, this has to do with restrictions, we'll talk about that in a minute, any of those quadrants can't be included. Also, it has to be, you can't sell half of a ski or half of a snowboard, things like that. So we can only sell wholes. So this solution region should actually be dotted on the integers. So these are all the combinations and I'll show you an example of that in a second, these are all of the combinations that can meet the manager's goals of having more than $600 revenue. So here's an example. I'll look at part E here. So hopefully that kind of helps you out with understanding the big idea here. Part E says, use your graph to determine a combination of ski and snowboard sales that will meet the manager's goals. Well, any of these dots will. So let's look at this dot, for example. That dot there in orange would be equivalent to 4 sets of skis and 2 snowboards. So 4 skis, because that would be $400, and 2, should say 2, no, sorry, that should say 6. 6 boards. That'd be equivalent to $720, and that's a total of $1,120, $1,120. That meets the manager's goals. There's all sorts of points. Would this point here meet the manager's goals? Yes. That point there would be 7 skis, 1 board. And you can see here that that would be $700, 1 board is $120, that would be a total of $820. So there's another combination. Any of these combinations, as long as they're in the positive plane and they're integers, would meet the manager's requirements. Now, I'm going to go backwards. So that's one method of doing it. You don't have to do any math as far as inequalities goes. Just setting up the boundary and understanding which side of the boundary works. The inequality, so if I go back to part B here, we could get the exact same thing with an inequality. So if we look here, it's a little bit trickier, but we'll get the same answer. Write a linear inequality to represent the situation. Well, we know, and I'm going to put this in pieces, that the revenue has to be greater than $600. And the revenue here would be $100 per pairs of skis plus $120 per snowboard. So the inequality that would actually represent this situation would be $100 for every pair of skis plus $120 for every snowboard. It has to be greater than $600. And you could actually then, let's look at part, we could graph that inequality. So we know the boundary. The boundary would be, and you're going to get the exact same part here, when 100 times k plus 120 times n is equal to 600. And the way we've done this before is if we sold 0 skis, so substitute 0 in for k, you get 100 times 0 plus 120n equals 600. So that's going to give you that 120n equals 600, and if I divide by 120, I get n equals 5. So when k equals 0, n equals 5. That would be this point right here. Okay, and vice versa. If we substitute n equals 0 into this function, you're going to get 100 times k plus 120 times 0 is equal to 600, which will then give you 100k is equal to 600, or in other words, k is equal to 6. So when n is equal to 0, k is equal to 6. That's that point right there. And because it's not or equal to, it's not included. The boundary line isn't included because it's not or equal to $600. It has to be greater than. So that boundary is not included. We're getting the same problem here. And if we use a test point, like we've done in previous lessons, if we test 0, 0 in here, you're going to get is 0 greater than 600, and that would be no. So you'd trade the opposite side. And the last thing to do here is apply the restrictions. So part D says, what are the restrictions on the variables? The restrictions would be whole numbers. Or in other words, there has to be a whole number of skis and a whole number of snowboards. It's another way to write it. And how do I know? Can't sell negative or part skis / boards. You can only sell positive integer of boards. So what that means again is that we're restricted to all these just integer values, these integer combinations of skis and snowboards, and not any of the negatives as well. So that's kind of the big idea of how we can apply this inequalities to word problems. And there's 2 methods.